Welcome viewers and subscribers. Welcome back to another video. JK Engineering and Architecture here, coming to you again with another engineering video. Now, in my last video, I have taught you how to derive the formula to calculate the bending moments for a point load acting at the center of a beam. Now, in today's video, I'm going to show you how to derive the formula to calculate the moment for a uniform distributed load. Now, in a subsequent video, I have stated to you that there are four main topics underneath structural engineering. And structural analysis is one of those topics. Now, structural analysis is very critical in engineering design, because before you can adequately design a structural system, you have to carry out the analysis. And that analysis will determine the reinforcement that should be designed to go into that structural member to withstand the impended loads. So in the engineering field, what we usually do first is to carry out an analysis and then we design. So if you watched the last video and if you're new to this topic, you might be wondering, why is it necessary to calculate the bending moments? Now, let me tell you what a moment really is in layman terms. So a moment is when a force acts up on a body and cause that body to be displaced or cause the body to move or shift, right? So we have to calculate the moments, because the moment is what is going to determine if the beam or the structural system remains stable. So the moment is what we're going to use to calculate the reinforcement to have that structural system remains in equilibrium and to establish stability. So if you follow my videos, you're going to see I talk about moments a lot. So the formula to calculate moments is really force times distance. And in future videos to come, if you keep watching, you are going to learn about moments some more. So in today's video, as I said to you before, I'm going to show you how to calculate or to derive the formula for a uniform distributed loads to determine the moments. So as you can see here now, this is a beam, and this beam is impacted by a uniform distributed load, which is the weight per foot. So a uniform distributed load is usually determined by the weight or the load per foot. So we take into consideration for every foot how much load or how much weight is attributed to that length. So the beam here spans a length of L, and this squiggly line here on top of the beam is what is described as the uniform distributed load, which is W per foot, or weight per foot. Now we have on this side, we have RA, meaning the reaction at A, and we have RB, meaning the reaction at B. So in order to calculate the moment, the ultimate moment for a UDL, we have to convert that UDL to a point load. So how we convert that UDL to a point load? We simply multiply the L by the weight, the length by the weight. So in this case, it will be L times W. So if you look to the right here, I have converted this weight per foot into a point load and let this point load, which is WL, act at the center of the beam. And if you're a physics student, you would know that weight act at the center. So the resultant of this uniform distributed load here is going to act at the center of the beam or at midspan. So we have here W times L, so we have WL here, so we convert this UDL into a point load, and the point load is active at the center of the beam. Now the length here is really L, right? And we're going to divide this L by 2, so at midspan we have L over 2 on this side here, and L over 2 on this side here. So L over 2 is just really half the distance of L. Okay? So, having done that now, I can now show you how to derive the bending moments formula. Now, having done that, so we have here now WL, right? So WL, so if we are going to find out the bending moments, the formula for bending moments, we have to plot what is known as the shear force diagram. And to calculate the bending moments, we have to draw the bending moments diagram. So in order to do that, we have to go back to this diagram here, because even though we convert it to a point load, we have to bring it back to a UDL. The purpose of converting the UDL to a point load is just merely to find the reaction. So the reaction here, and remember I've said it to you in my last video, if the load is acting at the center, half the load is going to act at the reaction at A, and half the load is going to act at the reaction at B. So the reaction here is going to equal to WL over 2, which is a half, and the reaction at B here is going to equal to WL over 2. So half WL over 2. And if you add WL over 2 plus WL over 2, you're going to come back to WL. Just let me give you a quick example of that. So in basic math, so we have here WL over 2 plus WL over 2, and we're going to add these two WLs here, and we must come back to our WL. Similarly, so if the load here was 10, the reaction here will be 5, and the reaction here will be 5. But let me just show you how I can add WL over 2 and derive and get back my WL. So this is going to be WL over 2, so the LCM is going to be 2. So 2 into 2, 1, we get back our WL here, plus 2 into 2, 1, we get back our WL here, right? So this is going to equal to 2 WL, because WL plus WL is going to equal to 2 WL divided by 2. 2 cancel 2, and we end up back with our WL. Right? So this is just to show you clarity. Right? So having found out the reaction here to be WL over 2, I can now go back to my diagram here and draw my bending moments and my shear force diagram. Now, to do that, I must carry back my weight here to be WL, because I have to put this back to calculate the shear force diagram. So our shear force diagram is going to look like this. Half the distance here. And of course, the reaction at RA is going to equal to WL over 2. And the reaction at B is going to equal to WL over 2. So our shear force is going to look like this. So this is the shear force diagram here. So, no, this is too close. Let me go down some more, because I want this diagram to be clear. Right? So, to draw the shear force now, we are going up. We have a reaction here of WL going upward. So, WL is going to come here. WL is going to come here. WL over 2 is going to come here. And this is the center here. So because this is a UDL, because this is a uniform distributed load that is going to span the entire length of the beam, the UDL is going to push down the beam like this. Right? So the shear force is going to look something like this. Right? And we have here, so at this point it's going to be 0. At the center here is going to be 0. And there's something I want to point out, that the maximum shear of any beam system, the maximum shear is always going to be at the ends. And as it moves along the beam, it's going to dissipate down or reduce until it reaches 0. So this force here is going up like this. And this is also WL over 2. So this is our shear force diagram for a uniform distributed load. And our bending moments diagram now, our bending moments diagram is going to look something like this. And at this point here is going to be the max. So to calculate the maximum bending moment, and to calculate the maximum bending moment, we are going to approach this in a similar way as I did for the point load. So the maximum bending moment is going to be at this point here, right? So the maximum bending moment, or the ultimate moment, or the moment, whichever you want to refer to it as, is going to be the area of this triangle, or the area of this triangle, because this system is in symmetry, so you can find the area of either of these triangles to determine the maximum bending moment. So bending moment is going to be the area of this triangle, and the area of the triangle, which we all know already, is half base times height. So the area of triangle is going to equal to a half base times height. So the moment is going to equal to a half, right, times the base. The base is going to be L over 2. And our height is going to be WL over 2. So the moment is going to equal to L times WL times 1. So it's going to be 1 times L times WL, and that is going to equal to WL squared. And 2 times 2 times 2 is 8. So our moment is going to equal to WL squared over 8. So our moment is going to equal to this, WL squared over 8. And WL squared over 8 is the moment to calculate the uniform distributed load acting on a beam. So in the case of my last video, the moment for a point load was PL over 4, and the moment for a UDL is going to equal to WL squared over 8. I could have gone ahead and tell you what the moment is going to be, WL squared over 8, but if you're a student and you're watching and you're in an exam and you do not remember what is the formula to calculate a UDL, you can simply quickly draw your shear force diagram and calculate the area, and you get your moment, which works out to be WL squared over 8. So this exercise, and if you're in an exam, as in when I was doing my exam, when you find the area, you do not need to plot the bending moment diagram, because you want to save time. So you quickly calculate your bending moment, WL squared over 8, and you can plug it in your formula to calculate your area of steel. So the bending moment here, which is the maximum, is going to be equal to WL squared over 8. All right? So to bring this topic home to you, I'm going to put actual figures to the calculation just to provide some clarity. So we have this beam here, and the span of the beam is 20 feet, and we have a uniform distributed load acting on the beam of 5 pounds per foot. That means every foot along this beam there is a 5-pound load. Now if you look at the diagram to the right, so what I have done is convert this uniform distributed load into a point load. So to do that, as I have shown you in my previous example, to do that is simply to multiply this 5-pound load by this 20-pound feet, which we end up with 100 pounds. And I have to put this 100 pounds at midspan, or at the center of this beam. So as I've shown you again in my previous example, if the load is 100 pounds acting at the center or at midspan on this beam, we have half the load which is going to act on the right and half on the left. So the reaction at RA is going to be 50 pounds, and the reaction at RB is going to be 50 pounds. And as you know already, 50 pounds plus 50 pounds, we ended up back with our 100 pounds. But we simply do that to carry the UDL to a point load, just to calculate the reaction. That's all that is all that is necessary to convert from UDL to point load. But to plot the bending moment diagram and the shear force diagram, I have to go back to my UDL. So we know that the reaction here at A is going to be 50 pounds. And the reaction at B is going to be 50 pounds also. So to draw the bending moments diagram and our shear force diagram, right? So to plot, and of course, if this beam spans 20 feet, we know that halfway along the beam, we're going to have our 10 feet here and 10 feet here. Similarly, in the previous example, we have L over 2. So the shear force right? So we have here 50 pounds going up. £50 going up. And then we have at midspan here, right? So because we have a UDL of 5 pounds and a distance of 10 feet at midspan, so to get the load here is going to be 5 pounds times 10 pounds, which is 50 pounds. And since we go up 50 pounds here, so at the top we're going to have our plus sign. I keep forgetting that. And the bottom we're going to have our negative sign. So because we have 50 pounds here going up and 50 pounds at the center, because 10 pounds, 10 feet, sorry, 10 feet times 5 pounds is going to equal to 50, right? 50 pounds foot. So 50 pound foot is going to come right at the midspan here. So we're going to have it like this, right? So 50 pounds is going to come here, 50 pounds foot. And so we have to carry through this. And then we are going back up 50 pounds. So we're going back up 50 pounds. So we have 50 pounds here too. And our shear force diagram is going to look something like this. Now I want to point out something to you, that in the event that you're plotting your shear force diagram and it doesn't close, that means you have done something wrong. So when you go up 50 pounds, right? And when you go up 50 pounds and you come all the way down and you're going back up 50 pounds, this 50 pounds here must equal to the reaction of 50 pounds here. Okay? So if you're plotting your shear force diagram and when you reach the end, the weight that you're getting at the end is not equivalent to the weight at the end of the reaction or the end of the beam, that means you have done something wrong. I might do a calculation with that in some time to come. So our shear force diagram is going to look something like this. Now our bending moments diagram now, our bending moments diagram is going to look something like this. And the maximum bending moment is going to be here. Now you might be wondering why your bending moments diagram looks something like this. And again, let me give you a demonstration. So if this is your beam, right, and you have a uniform distributed load spreading along the beam like this, and you have two reactions at the end, one here and one here pushing up at either end, and the load is pushing down, you're going to get a curve like this. So if this ruler was flexible, I would have shown you how it will look, but it will look something like this with a curve at the end. Alright? So that is your shear force diagram and that is your bending moments diagram. So to do a quick recap, the load or the force that you're getting at the end of your shear force must be equivalent or equal to the load for the reaction at the end. So if you notice I have 50 pounds here and it comes up to 50 pounds here, that means it is closed and my diagram is correct. Now to calculate the shear force diagram, the bending moments for the shear force. Now, as I said to you before, to calculate the shear force diagram, the bending moments diagram, the bending moment should say, is going to be the area of this triangle or the area of this triangle, which is half base times height. So the area, so the moment is going to equal to a half times the base, and of course the base is, this is going to be 10 feet, and this is going to be 10 feet. So the base, which is going to be 10 feet, times the height, which is going to be 50 pounds. And the moment here is going to equal to 250 pounds foot, because half of 10 is 5. 50 times 5 is 250. So this is going to equivalent to 250 pounds foot. So the moment, the maximum bending moment at this point here is going to equal to 250 pounds foot. So if you're going to design the reinforcement for this beam, the moment that you're going to use to put in your formula to calculate the area of steel is going to be 250 pounds foot. Now, to bring this home to you now, and that's why I said it's important for you to know the formula. If you know the formula, you do not have to go through all of this. But this still is very important, because if you get a beam to design with a point load which is off center and a point on a UDL which is off center, you need to go through this format or this process to plot your shear force, to plot your bending moments diagram, and to calculate your maximum bending moment, so that you can use the result of that to calculate your area of steel. But for this exercise, and since we are only dealing with a uniform distributed load, and I've already shown you what the formula is to calculate a uniform distributed load, it is the moment is going to equal to WL square over 8. So if you use this WL square over 8, you should come back to this 250 pounds foot. So let's do it. So the moment is going to equal to W, which is the weight, which is 5 pounds. 5 pounds per foot, times L square, and the length here is 20 feet, which is 20 feet squared, over 8. So this is going to equal to 200, because 250 pounds foot. So 20 square is going to equal to 400. 400 times 5 is going to equal to 2,000, and 2,000 divided by 8 is going to equal to 250 pounds foot. So that is the reason why I've said to you that it's important to know the formula, so that you do not have to go through this. You can just simply use the formula of WL square over 8 to calculate your ultimate moment or your maximum bending moment, and you do not have to go through all of this. So that is it for this video. The next video I'm going to look at cantilever, so make sure to tune in for that video as well. So I have come to the end of this video. So remember now, as usual, for my regular viewers and subscribers, you know the drill already. If you're new to this channel, make sure to hit the subscription button, hit the thumbs up button, and give me a like, and I'm going to catch you in another video. Enough respect.